And welcome back as we continue our cosmic journey. Let's go ahead and take our segue by diving deeper into the small things by looking at the structure of an atom. So as we start probing the atom to really find out what is the components of this item, we have to first understand that the idea of an atom is composed of tiny particles, and this idea has been around for at least 25 centuries. I've always said, like, well, there's a small thing, the smallest thing is around. But it didn't really take until the 20th century for scientists to invent instruments that actually allowed us to probe inside an atom and discover that, hey, there are smaller particles inside us. Like, we knew there were things like iron and tin and stuff like that, but until we could actually have the tools to be able to look inside those, we weren't able to really formulate what made an atom an atom. Now, the first of these smaller particles, which was the electron, was discovered by British physicist James Thomson in 1897. This particle is negatively charged. Because an atom in its normal state is electrically neutral, it means it's not an ion, each electron in an atom must be balanced by the same amount of the positive charge. So let's actually just figure out, how do we find these charges? How do we actually know that electrons exist? Well, the next step after discovering that we have electrons is to determine where in the atom the positive and negative charges were located. In 1911, British physicist Ernest Rutherford devised an experiment that bombarded an extremely thin piece of gold foil with the beam of alpha particles. Now, alpha particles are helium atoms that have lost their electrons and therefore are positively charged. And in the experiment, as you can see here in this diagram, you have this beam of particles that was shot out at the really thin gold foil here. And what happened is a very small number of alpha particles were significantly deflected back, whereas a few alpha particles are significantly deflected off in other directions, but most of the alpha particles would pass straight through the foil. And again, this here is just a diagram of looking at that atom. And you can see here we have a hydrogen with 2 electrons. So that allowed Rutherford to start analyzing results. Now, most of the particles, as we just saw in the diagram, passed through the gold foil just as if in the atoms were in nearly empty space. About 1/8,000 of the alpha particles, however, completely reversed direction and bounced backward from the foil. In other words, they came right back to the direction they were sent. Now, the only way to really account for the particles reversing is when they hit the gold foil is to assume that, well, something has to have mass, or as well as the positive charge in each individual gold atom has to be concentrated in a tiny center or a nucleus. Now, when a positively charged alpha particle strikes a nucleus, it reverses direction. Now, Rutherford's model placed the other type of charge, the negative electrons, in orbit around this nucleus. So let's actually look at Rutherford's model here to kind of try to establish what this means. Now, his model required that electrons be in motion. Positive and negative charges would attract each other, so stationary electrons would end up falling into a positive nucleus. And because both of the electrons in the nucleus are extremely small, most of the atom have to actually be relatively empty space, which is why nearly all of Rutherford's particles were able to pass right through the gold foil without colliding with anything. Now, Rutherford's model was a very successful explanation of the experiments he conducted. Now, though eventually science would discover that even the nucleus itself has some structure to it. So let's examine a little bit further. So with that nucleus, the simplest possible atom we can have is hydrogen. Now, the nucleus of ordinary hydrogen contains a single proton and a single electron, as we can see here in this diagram. The mass of an electron is nearly 2,000 times smaller than the mass of the proton. So that means electrons are very, 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 very small. Now, the electron, even though it's so small, carries an amount of charge exactly equal to that of a proton, but opposite in sign. Well, that's all fine and dandy for hydrogen, but let's look at this with another atom to really kind of reinforce what we're talking about. Helium is the second most abundant element in our own sun, hydrogen, of course, being number 1. Now, helium has 2 protons in its nucleus instead of the single proton that characterizes hydrogen. In addition, the helium nucleus contains 2 neutrons. These are particles that have mass comparable to that of the proton, but they have pretty much no electrical charge, which is why we say they're neutrons or neutral. Now, moving around this nucleus are in the helium 2 electrons. So because we have 2 protons and 2 electrons, the net charge of the helium atom is also going to be 0. Now, you might have guessed that the pattern for building up all the elements that we find in the universe here. The type of element is determined by the number of protons in the nucleus of the atom. So an atom with 6 protons is the element carbon, 8 protons is oxygen, 26 is iron, etc. Now, atom has the same number of electrons as protons, and these electrons follow complex orbital patterns around the nucleus. Now, deep inside of stars, however, gets to be so hot because of the very high temperatures that are there, that electrons actually get separated away from the nucleus, and as we can see here as we start exploring a little more, lead separate yet productive lives in part of their existence. So let's look at the other components that we can have in an atom. Now, the ratio of neutrons to protons increases as the number of protons increases, but each element is unique. The number of neutrons is not necessarily the same for all atoms of a given element either. In fact, most hydrogen atoms, as we already said, contain no neutrons at all. That's simply just a proton and an electron. There are, however, hydrogen atoms that contain at least 1 proton and at least 1 neutron. And there are others that actually contain 1 proton and 2 neutrons. All right, and these various types of hydrogen are what we call the isotopes of hydrogen. So if we look over here, we have hydrogen, just plain old regular hydrogen, and you can see there's just a proton, there's no neutrons, 1 little lonely electron hanging out here. Over here, we have that first isotope of hydrogen, and again, we have a neutron. Doesn't change the charge at all. This is still a positive and a negative charge. But then if we move over here to the second isotope, again, now we have 2 neutrons, and we have, again, the same charge here. So the charge is the same. It doesn't change because, again, neutrons have no charge, but we have 1 electron, 1 proton, and these, of course, are 3 different isotopes that exist with hydrogen. Now, there is an issue with the model that we've been looking at. Rutherford's model for atoms has one problem. If we go and apply Maxwell's theory of electromagnetic radiation, it says that electrons change either speed or direction of the motion. They have to emit some kind of energy because, there's a change. Well, orbiting electrons constantly change their direction of motion, so they should emit a constant stream of energy. Applying Maxwell's theory to Rutherford's model, all electrons should eventually spiral into the nucleus of the atom as they lose energy. So that prompted us to have a need for a new model. Physicist Niels Bohr solved the mystery of how electrons remain in orbit. He was actually trying to develop a model of the atom that would explain certain regularities observed in the spectrum of hydrogen. Bohr assumed that if the electron moves in allowed orbits, it radiates no energy. If its energy would change only if it moved from one orbit to another. In Bohr's model, if the electron moves from an orbit to another closer to the atomic nucleus, it must give up some energy in the form of electromagnetic radiation. If the electron goes from an inner orbit to one that's farther away from the nucleus, well, it's going to require some additional energy. Now, one way to obtain the energy, of course, is to absorb electromagnetic radiation from an outside source. And that's going to get us into looking a little bit at electron orbits. We're not going to get too much into the nitty-gritties of it, but a key feature of Bohr's model is that each of the permanent electron orbits around a given atom has a certain energy value. So if we want to move from one orbit to another, it's going to require a change in the electron's energy. If we want to move to a lower energy, the energy level difference must be given off. We have to shed energy. If the electron goes to a higher level, the energy difference must be obtained from somewhere else. So we have to gain energy. Now, each jump or transition to a different level has a fixed and definite energy change that's associated with it. So here we actually have one of the situations where it's easier to think of electromagnetic radiation as particles, so photons, rather than as waves. As electrons move from one energy level to another, they give off or absorb little packets of energy. When an electron moves to a higher level, it absorbs a photon of just the right energy. That photon and wave perspective that we've been discussing must also be equivalent, because at the end of the day, light is light no matter how we look at it. That's going to get us into one of our last concepts, which is this of Planck's constant. Each photon that is emitted has a certain amount of energy that is proportional to the frequency of the wave that it represents. The value of its energy is given by the formula E equals hf, which is of course known as Planck's constant, named after German physicist Max Planck. Consider a calcium atom that might exist inside the sun's atmosphere, in which an electron jumps from a lower level to a higher level. To do this, it needs about 5 times 10 to the minus 19th joules of energy, which it can absorb from a fascinating photon from deeper inside the sun. Now, this photon is equivalent to a wavelength whose frequency is about 7.5 times 10 to the 14th hertz, and whose wavelength is about 3.9 times 10 to the minus 7th meters in the deep violet part of the visible light spectrum.